Thank you to everyone who joined. I know most of you. Guido, I think this is the first time we know today, so pleasure meeting you. I think we'll just start. So thank you, Barca, for running this meetup. Barca is a developer advocate at StarTree, and she's doing plenty of other stuff, other things, the technologist enthusiast, like putting women at the front. She's doing a lot. So I invite you also to check her LinkedIn and connect with her there. And yeah, indexes with Apache Pinot, that's the topic. And Barca, I'm heading it to you.
Thank you so much. I appreciate your kind words. And yeah, so let's get started with the indexes with Apache Pinot. Some of you may have seen some other presentations on this. My take on it is a little different, so let's get started. This is the agenda. I'm going to talk about search for a minute, not too much. Then I'm going to talk a little bit about indexes, back to basics, and then I'm going to talk about the Apache Pinot indexes. We'll talk about some use cases and the demo. So the demo is where, ask questions. Let's discuss your use cases, and at the end we do have a t-shirt giveaway. So we'll share that with everyone as well. As Yarden said, my name is Barca Herman. I'm the developer advocate at StarTree, and let's get started. This is the first statistics that I have. With around 5.35 billion internet users worldwide, each person can potentially generate 15 terabytes of data. So the point here is that the data collection is not going to slow down. And as we're creating more and more data, databases of tomorrow have to deal with this data. So how does one go about searching stuff in this much data? So let's talk about search for a little bit. So this is a question I used to ask when I was doing AI model. If I were to ask you to find the highest peak on Earth and you were looking for it, how would you go about doing it? So, I have three ways of looking for it, but I'm interested in hearing how you would solve for the problem. The brute force method is like you just climb every peak in the world and then discard the one that's lower. And so this is kind of like your selection sort of bubble sort kind of algorithm, where you're just climbing all the time. This is very slow. It takes forever. Or you could do things like create a team of n number of people, and each one finds like a local maximum and then comes back and then compares nodes. So this is what we're talking about in database methodology: distributed search, distributed data, the peaks are distributed, of course, but also distributed compute, because it's not the same person serially climbing every peak. So we're talking distributed compute. There's also another way, which is anticipate someone is going to need. This, my friends, is indexing, right? So indexing is, hey, we know which is the peak, what is the height, so let's put it somewhere so we can point to it. And then, of course, a more organized way of doing things would be send an altimeter with every climber and keep recording it. So as we're ingesting data into a database, this case would be we organize it as it comes in. So that's the way I see search as. So let's talk about indexes, right? So originally, the indexes used to be, we had one large data file comprised of records. A set of records had many pages and then the page boundary is based on how much data can we load into memory at one time. And typically it was like one page at a time. And so there was this arbitrary limitation on how many records you could search at a time. And then file, it's organized by something. So another way to organize it is that, you organize files based on something. So something is the key. So you have one key and the entire file is organized by that key, which is the dictionary, right? So only one of these is possible because you cannot reorganize using multiple keys. You could do complex keys, but it's still one thing. So the file is this monolith and it's ordered by a key, and that's it. And then you could add, external, not to the file, but data structures within that file with pointers to have other records. So this is the other way of indexing. So I'm going to pepper my presentation with some of these crazy information. So IMS, the first hierarchical database, was created in 1962 for the Apollo project, by the way. Did you know that? I didn't know that. So in other words, what I said in the other slide is that you have two types of indexes. You have clustered and non-clustered. So clustered is a dictionary type thing, and you can only have one. And then non-clustered, you can have many indexes, and you can have two patterns of searching. One is a dense index, which is you have a data structure that has a key, and the key points to a record. Or you can have a sparse index, which is a data structure that has a key, and the key points to a block that has multiple records. So you're doing two-step lookups. It's not a key value kind of thing. It's more of a key points to a region, and within the region, you may have another data structure, or you may just go through that, section to find the record you're looking for. And then, of course, you have multiple types of algorithms that you can use in any of these. So you can have a key value pair, which is the dense record for non-clustered. You can also have bitmap or trees. And we'll talk a little bit about it when I go into the Apache Pinot context. By the way, 1972, E.F. Codd paper introduces the first relational database. Believe it or not, a lot of times when I talk to people about NoSQL, they assume that NoSQL is new. Every database before 1972 was NoSQL database, non-relational. Okay, so enter Apache Pinot. This is what we're here for. Why are we even talking about this search and index and all this basic stuff? I want to talk about Apache Pinot indexes and how Apache Pinot elevates indexes. So here's a look at all the different flavors that indexes come in. So we have Bloom filter forward, FST, geospatial inverted JSON range, text search, timestamp, and vector index. I have slides on most of these, but I don't want this to become like a, hey, rehashing of Apache Pinot docs. So I'm not going to go into each one of them in details, but I'll give you some important things to remember when you're using these indexes. But before we go into that, there is an important paper in 2005 that Michael Stonebaker et al. Introduced on columnar databases. And yes, Apache Pinot is a columnar database. So the reason I kind of set up the whole story the way I did about the monolithic records and then also the page boundaries and all this stuff is because I wanted to introduce why indexes in Apache Pinot are so effective. One of the reasons is it's because it's a columnar database. And of course, columnar databases work much better for OLAP than OLTP, because in OLTP, we want to optimize for writes. In OLAP, we are optimizing for aggregation. So what does that mean, right? First of all, every index can be clustered, because if you see the image on the right, you have a chunk by date. Obviously, if we're organizing dates, it may be, new first or last first or whatever. So it's ascending or descending. But you may want to organize price very differently than you do date. Columnar databases allow for clustering to happen. So in other words, sorting or ordering to happen in every column. So it's not limited to the key column. Point number one, right? Point number two, when you're doing aggregations, you're not bringing the entire record into memory. If you're grouping by date, you're only bringing the date columns in memory. So it's using lower memory. So it's much more efficient. And this is why it is great for aggregation. So I'm going to go through these fairly quickly because Oh, I see some comments. Very clear so far. Andy Powell also did an update on Stonebaker paper. Awesome, awesome. So I'm going to talk about some of the indexes, and especially if you're using large data sets, you understand that, writing small sample data and running queries doesn't show anything, like doesn't prove anything because the queries will be effective. But you're doing terabytes or multiple gigabytes of data, then every little bit matters, right? So the Bloom filter is best for equality. And the reason is because if you use the Bloom filter algorithm, it gives you where things are not. So when you're searching a segment, it can tell you, oh, if you're searching for, let's say, name equals Robert, it will tell you, oh, I definitely know that it's not in segments 3, 6, and 5 or whatever. So that's how Bloom filters work. And that's why it's very powerful and it's useful when you're using equality a lot. If you're not using a lot of equality in your queries, then you can skip Bloom filters. Okay, FST, regex-based search for text fields. So that's FST. It only works on completed segments. So in other words, if a segment is consuming, it's probably not going to work very well. And it works, it uses dictionary encoding. So encoding is another feature that Apache Pinot has, which is very powerful because you can either have a dictionary, which is key value pairs, or you could have a sorted database. So you have the columns sorted by something, or you can have a sparse dictionary. So dictionary points to something and it points to another segment. So those are different ways. And then there's raw encoding also. So encoding helps in the speed up. It's not part of the indexing, but it is. When you define an index, you also define indexing, encoding, sorry. So FST is a leucine-based index. It's case sensitive and it uses supports regex. The forward index, it's a mapping from a document to content. So doc1 has word 1, word 5, blah, 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 right? And it supports, this is what I'm talking about, the sorted dictionary and raw value. And of course, the implementation. There's good use cases for all three implementations. All right, so inverted index is the other way. So forward index is useful. It says, hey, I have a document. In the document, what are the words, right? That's great. But it's better to say, hey, I have a word and I want to know which documents it is. So documents in this case maps to segments. So if I'm looking for W1, word 1, I know that it exists in doc3 and doc4. So this index is fast. Now, there's two ways to implement this index also. There's a sorted version of it, which makes sense. And the bitmap one is useful because let's say that you have limited set of values possible, like yes or no. You can have a bitmap that kind of tells you, hey, where all the yeses are, where all the nos are. It's not recommended for varied data, but it's recommended for limited types of data. Yeah, Peter says my Red Sox are not in my closet. I already checked. Why we need Bloom filters in real life. Absolutely. That's a great example. I'll have to remember that one. Okay. And of course, you can take the inverted index to the next level by creating range indexes. So, we do a lot of time series type data, and it makes sense that rather than saying, hey, at this second, the record is this, at that next second record is that. If you use a range index, you can say, hey, from time X to Y, the records are in document 1, right? So you can see how it optimizes query times. And it's really great for range-based searches. So greater than equal to type of searches, it's perfect. So that's what that is for. Of course, we have geospatial index. So this is a mapping of the hexagons of the Earth. And it supports the OGC OpenGIS specification. And it's really Uber's fault that we have it. And then, of course, we have JSON index. This is mapping nested values. It's great for fast searches on nested data, which is typically what JSON data looks like. And the star of the indexes is the StarTree index. And basically what this is partial pre-aggregation. So instead of pre-aggregating all the data, so this, this example, this diagram is based on, let's say, you have a website and you want to track the traffic that's hitting the website based on country and browsers. So let's say that the D1 layer is countries, and then the D2 layer is browsers. So let's say that 90% or let's say 80% of your traffic is coming from US and Canada. And, the rest of it comes from the rest of the world. So not picking on Kiribati, but how many hits from Kiribati? If you start creating a bucket per country, it may get tedious to create them, maintain them. So the way StarTree Index works is that it'll, give you cubed version of 80% of your data, which is the D1V1 and D1V2, and then everything else goes in the star bucket. And then it can work on multiple levels. So the next level might be a browser. So the browser, it may be Chrome or, I'm using Brave. Use your whatever favorite browser. There are hundreds of browsers now. Those all end up in the star bucket. So depending on traffic. That's the StarTree index. And then finally, I can stop here because we do support vector index in StarTree, which is what we do is we store embeddings, and the searches are based on nearness. Give me the top closest things to this embedding, right? So you can do that. We will be seeing a lot more of embeddings used for searches moving forward. We're already doing that in like search. When you go to Google or whatever, they are using embeddings to do some searches, maybe not all. But we'll be seeing more of this in as time goes on. All right. So with that, I'm going to go towards a demo. So let's talk about this demo. Okay, let me know if you can see the screen still.
Yes, we do. And I see a question from Hernando Barca. Is there any kind of a publication discussing ingestion and indexing performance?
Yeah, there was a series of blogs that were written on indexing, and I'm happy to link those in the chat shortly. I don't have them on me right now, but I can find them for you before the end of this session. Also, if there's something specific, Hernando, you're interested in, we'll write something for you. So. Okay, so I want to talk about this. So this is a 6.39 gigabyte of table size of data. What it is this ride sharing data. This is ride sharing from I think this is Chicago, right? I forget. Yeah, Chicago taxi data, or is it New York taxi data? I don't know. But this is publicly available data that we ingested, and we're going to run some cool queries against this. So let me open this in a new tab. So this is the query window. And I wanted to share this with you just so you know that, it's a substantial amount of data. And then we'll also talk about a little bit as we do run the queries, we'll talk about how it's working. You'll notice that we have indexes defined here, and we'll go back and forth between the two tabs so you can see what I'm talking about. Yeah, right, sharing. This is the one. All right, so let's run some queries. So you can kind of see what is going on. There's like 196 million or so documents, total records. And these are some of the fields. So we have, you know, where did it start from, where it end, when did it happen?
Hey, Barca,
And
there's a question from the audience. Could you just walk through the table config just for a little bit?
yeah, I wanted to come back to the table config to illustrate what we were doing. So this is the offline table. So we have the ride sharing, the table name, table type. And then we have some data as far as segments. So there's a retention period, push type, all this stuff, right? There's always a time column name because we do organize based on it's time series data, right? So we organize based on time. And you know, we have tenant definition. Again, it'll make more sense when I run the query to explain what's going on in the config. So let me run a couple queries first real quick, and then Robert, I'll definitely show you what. Okay, so let's look at this query. So this is what we're doing is we are doing a conversion right off this. So as you know, when you're doing conversion on 6 gig of data, that'll slow things down. But we also have things like averages and mins and maxes. Now, it is my contention that the average min maxes are very performant on Apache Pinot. So let's take a look at whether I'm right or wrong. So this is using no indexes for the time. And that's going to take a minute. Okay, so we got, you know, this is how long it took, and we got some results. So what it has done is it's taken the daily aggregates for the entire data set. So we have several days worth of data, and it's giving you some average distance, average travel time, minimum, some mins, maxes. So a lot of aggregation based on date. Of the entire data set, okay? Now I'm going to use an alternate. So keep an eye on this first portion. And what I'm doing is that instead of using that conversion, I'm using a already converted data. So somebody had talked about ingestion, right? How to do injection. And by the way, we're not using StarTree. So let's run this. And you'll see that the time used was much better. The performance is much better. Now, we have inverted indexes on many of these. So let's go back to the to here and see why that was more performant. So first is converting 196 plus million rows is slow, but also let's look at some of the ingestion config. So what we're doing is we are doing the conversion during ingestion. Where are you? Yeah, so this is the transform function, which is making it so that we are not doing the conversion at query time, we're doing it at ingestion time, and that makes a ton of difference. So that's point number one. Point number two is, of course, the index config. So let's take a look at where are my indexes. And here's the inverted columns. And so as you can see that we are, the trip start date is using an inverted index, and that's one of the reasons why it was so effective, so fast. So again, going back to this query, trip start date, and then also the trip miles, trip seconds, they don't have any indexes, but the roll up is happening super fast. because of that one inverted index on the trip start date. Does that kind of answer your question, Robert?
Partially. I was
Okay.
curious about the configuration of the StarTree index, but
Yeah. Okay.
you're highlighting here that you have an inverted index on the start date, and
Correct.
I wonder about the cardinality of the data.
Yeah. So, I paid him to ask that question, by the way, because what we're going to do next is actually use the StarTree index and run the query, and boom. So using StarTree index obviously will speed up things. So let's take a look at my StarTree index configuration. Where are you, buddy? There you go. So the StarTree index is using trip start date, month, and year. I have a couple other queries that I have. So did you mean cardinality of the StarTree index split order, or did you mean something else by that?
I meant the cardinality of the start date column. If the cardinality of that column is high, wouldn't that have caused issues for the inverted index?
Okay. Complete disclaimer here. If you notice, there's not that many days that we have imported in this data set because it's a huge data set, right? So the trip start date, there's 196 million rows, but for each, you can see that they're subdivided into this, I don't know how many there are, like 15 or so dates. So it's a low cardinality from a trip start date point of view. And that's how you want to organize your StarTree indexes, because you do want the buckets to be kind of, not individual things. So in my lame example in the slide deck, it was like countries and browser types. And we're talking hundreds. We're not talking millions, right? So that's what makes it faster, because you don't want a bucket containing of 10 records each, which is really not, what's the point of that kind of aggregation? Does that make sense, Robert? Does that answer your question at all? Yeah.
Yes, it does, because it's only at the day granularity, so the cardinality is low.
Correct.
If it was like you were using an epoch timestamp and your granularity was milliseconds, then it would be an issue.
Yeah. And then, in reality, you don't need to do a roll-up of the epoch, because if it's a millisecond, how many records can there be a millisecond? Even if it's 100, because of the segmentation, the way we do it, a range index could handle that, right? Does that make sense? Because it's sequential, right? It's a time series data, it's sequential. So for every second, you can have a second segment or whatever. Does that make sense? Yeah. Yes, no? It makes sense to me. Okay. Let's do some more queries. All right, so here's another one. So this one is also, now this is daily aggregates without ingestion time transformation. And it's going to take a minute. It may even time out. Yeah. Let me put that timeout here. And make sure that I'm not. So a similar performance. And this is, as you notice, this is not taking, making use of that inverted index. And then let's do the inverted index. And we don't need that timeout because this is going to be fast. And we can run this with true. And you'll see that it's amazingly fast. So same thing there. Yeah, so in this data set, we're not doing that much fine tuning. So the question Robert has is that, are we doing any fine tuning of the index? This data set, we're not doing any fine tuning. This is just a demo data set. And believe it or not, it's a small one, right? So the fine tuning would happen based on the query patterns that are, that we're seeing against the data set. So StarTree index, we don't recommend creating a StarTree index right off because of the fact that we don't know what patterns are being queried most of the time. And then once we are familiar with the patterns, then we can optimize and also do some more fine tuning. This is just a demo data set, so it's not fine tuned. And then finally, I want to do yearly. So if you notice, we also have a year field that we defined. So let's run this query.
And there's a question from Robert. Did you do any fine tuning of the StarTree index?
Yeah, I think I answered that. Yeah.
Yeah, thank you, Yarden. That question was already answered. I was wondering
Okay, sorry.
because I remember that the StarTree index only performs pre-aggregation if a sufficient number of records falls within that bucket.
Yeah, and that, again, to your question about the cardinality, right? So again, if it was by epoch, it wouldn't make much sense. So, and that's why the cardinality is different here. So this one is, again, this is year-based thing. This is not daily aggregation, this is yearly aggregates. Oh, wait a minute, it's not. I'm lying to you. So this is the yearly aggregate, and yes, we are actually converting it based on the original field. So we're using a function on every record, 196 million records. And yeah, it's slow. And then we'll use our inverted index by using the field. So this one uses the trip start year field, which is using an inverted index. And immediately you see that the time drops. And if we change this to true, it is single digit, which is amazing. I mean, I think we need applause for this, but it's very impressive. So as you can see, the indexing makes a lot of difference, and it makes a difference because of the, what kind of data, what kind of buckets, what kind of queries you're running. I don't have like a demo for a Bloom filter type thing or anything like that, but you can kind of see how each index type is super powerful based on the query patterns that you are seeing in your data, and also which index goes for what. So at this point, no. So a good question, Hernando. The question is, are we seeing caching effects in your demo queries? That's not the case. This is, I mean, it's as simple as we're querying a different field, right? So I wonder if we can, let's do month, because I haven't run a month query, right? So let's run it in a reverse. And so we're going to use the StarTree index first. Oh, it would help if I actually have a valid query, right? So, okay, so we got month. So this is the StarTree index. according to our, the caching, this should be faster because it may be cached already. Not so, not so. And then we can go back. So this is evidence that it's not a caching thing that's causing this. It's actually using the StarTree index. So, I mean, you can imagine a pre-aggregated query will be much faster. So, yes, it is caching, but it's a very different type of caching. All right. So, any questions about this, and any questions about what we're doing as far as the indexes and the power of the indexes that we're using here? And also the other question that I wanted to mention was that I wanted to show that the transformations happening during ingestion make all the difference also.
Yeah, hi, Joel here. So if I want to start using Pinot on my own computer, how would I do that? Is it possible to install it on my Windows PC? And if not, what's the sort of best place to start at that is not expensive?
Right. So there are great question. Again, I paid this guy to ask me this question. Kidding. So I am a Windows user. So I run, everybody else in the company uses a Apple, and I purposely make sure that all the examples and everything works on my computer. And so if you go to dev.startree.ai, as a matter of fact, let me see if I can bring it up here. Dev.startree.ai. You will find that this is how you would do it, right? So you can just run a Docker container, you copy the code without the dashes, and then it'll work. And to prove that I'm not making this up, let's bring up Docker desktop, and it'll show up. And here's all my little images and everything, and I do this all the time. So I run it very easily. So that's for free, but there's another way of doing it for free. And that is by going to startree.cloud. So this is a cloud hosted free tier option that you have, and you can just sign up here. And can you guys see my screen?
Yes.
It's free forever. Yes, it's free forever. Of course, you are going to be in a cluster environment that's shared. So if you want to run it for performance, then this is probably not the way, but it's definitely good enough to give it a try and do a lot of stuff. So I have a cluster that I created under a different email than my work email, and it's got some 30 meg of data, and I do prototyping and things like that on that all the time, and it works beautifully. So good question. Thank you.
Thank you very much. Well answered. Thank you.
Can we take a look at the StarTree index config? I
Yeah.
didn't quite catch that.
All right, so let's go here. And let me see. Where are we? Yeah, there you go.
45. Yeah.
So let's talk about StarTree index again. It's, I showed you the image, and the image is kind of confusing, but basically now, what we're saying is we're indexing, we're creating pre-aggregated buckets for three fields: trip start date, trip start month, and trip start year. And so it's gonna go ahead and create these buckets. These are going to be pre-aggregated, and they're hierarchical. So the split order is date first, month next, year next. So that's how it's going to be used. So Hernandez says, very large data set size in production, what size say? So this is a 6.39 gigabyte demo set. So you can imagine. I was talking to Guido earlier, and he was talking about how they're using 100 gigabyte plus data sets. And one of the Apache Pinot customers is Stripe, and they have terabyte and petabyte data sets. So very large data sets. If you've used LinkedIn, pretty much every page on LinkedIn is using Pinot dashboards. And so your LinkedIn feed, your who viewed your profile, all those are dashboards. Uber Eats uses it for all their apps, and they have large data sets. So the data size is not an issue here.
What if the order that you specified the columns in and dimension split order was different? How would that affect the query performance?
Yeah, it would. So, it's this is why the fine-tuning happens based on existing queries. If you think about this query, this order, the reason why it makes sense is that, if you want to go to the trip start year, then it's just adding up all the, you can go down that path and just use that. Whereas, so the year bucket is on top, and then the month and the date. So the most used thing might be date, but the year is just an aggregation of that, and month is just an aggregation of that. And because we're using inverted indexes, you don't even need all of it. So again, this is a demo StarTree index implementation. In reality, chances are that these buckets will be completely unrelated, right? So like website, a country, and browser are probably very unrelated. It's not a typical date, year, month kind of thing. So in that case, what you would design it based on is the most queried on top, and then the next stuff below that. So if you have more queries against the country versus the browser, then that's the hierarchy, and so on.
Why is that? Why do you want to specify like the date first, an example? Why is that? You're saying that that queries for the date are more frequent, but how does that relate to like how
this is like
the performance is affected?
My answer is I would never do a trip start date, month, and year, because if I have a pre-aggregated thing for date, then month is adding up 30 of those, and Pinot is really good at aggregating, aggregating numbers of 30 buckets. It's easy. And then a year is only 365 of those. And so Pinot is very good at adding up 365 records. So this is not a good example, is what I'm trying to tell you, is that the better example would be something unrelated. Does that answer your question, Robert?
Hopefully next time we can look at a better example.
Yeah. And again, this is a demo. And the reason we chose this was because it's a lot of data. And yeah. Awesome. Any other questions? Are we excited about?
I was trying to write on the chat, but I guess that I'm wrong with something. The idea I want to ask about hybrid tables on the Pinot index. The functionality is the same. You talk about the offline table on a hybrid table. Is the same benefits to use the StarTree index?
Yeah, so that's a great question. Yes, a hybrid table has both real time as well as the offline tables. The thing about the real time stuff is those are coming in as we are processing it, so it'll be current in a segment. So those queries are fast anyway. The StarTree index works really well in offline tables because of the vastness of the data. If you're just interested in the last hour or last minute, depending on your segment size and how much data you're ingesting, that's one segment. So I mean, I'm not saying it's bad, but the performance is great anyway.
It's as good as offline table.
Right.
Okay. Well, there is no problem blending data with those kind of index, right?
Correct.
Blending data online, offline. Okay, thanks.
Correct. Any other questions, guys? If not, I'm going to stop sharing. And we can just come on camera and ask. So, yeah, good. Who's gonna implement this stuff? Yeah.
I'm sure everyone will.
Yeah, there you go. Awesome.
And thank you, Barca.
Yeah.
And I hope everyone got the chance to scan the QR code Barca shared. It was the last slide. If you want to get a chance to get into a raffle and get our limited edition exclusive community t-shirt, so just sign up. Yeah, and you will get into the raffle. And we
You
will.
have an international ship?
Yes, we do. Yes, we do. So it's basically like you can claim the t-shirt from our swag store, and it has a worldwide distribution. So no worries.
Oh,
Yeah,
can
Yeah,
you show again the QR, the code? I couldn't catch it.
absolutely. And yeah, Robert, yes, it does work on offline tables, of course, because if it's just online segments, those are smaller anyway. And appreciate your kind words, Hernando. And hopefully everyone learned something. I know Robert's been using Apache Pinot longer than I have. So hopefully you did learn something as well.
Thank you, Barca. It was great, and it was great seeing you all. And we will meet on the next meetup. Thank
All right.
you.
Thank you,
Sounds good.
Raga.
Bye bye.
Thanks, everyone. Have a nice week. Bye-bye.